Hello, everyone. This is the second part of lecture 2 for dynamic programming for 6047, 6878, and HST 507. We were interrupted in the third part of dynamic programming for sequence alignment, specifically going through the key insights. Number one, that the score is additive, so we can solve smaller problems than larger problems. Number two, that the score can be computed recursively. Number three, that the subproblems are repeated, and therefore we can reuse the computation when we're going to need it. And number four, that we're using this bottom-up approach that allows us to now have the optimal alignment score stored in an ij position of an end matrix that basically stores the score of the optimal alignment, which then allows us to go through and use a maximum operation, choosing between three different options of whether we're using a match or a mismatch, a gap in one sequence, or a gap in the other sequence. As we fill out this matrix, we end up at the bottom, and that gives us a full alignment of a path through that matrix that corresponds in a one-to-one fashion with an alignment. So we're iteratively growing the best alignment, computing the alignment recursively, and then setting up the matrix for parameterization using a simpler 2D matrix rather than looking at all possible subsequences of I, J, K, L for-way indexing. We're actually using IJ indexing of only prefixes rather than all possible subsequences. We're making sure that the subproblem space is finite. It's only an n-squared number of computations, which is polynomial and exponential. The traversal order enables us to always have the upper lefter and upper lefter matrix entry already available. And then the recursion formula effectively allows us to compute Mij as a function of the previous results. We're only doing a single increment at a time. We're only looking at the I-1, the J-1, and the I-1, J-1 positions, corresponding to three options. And then we're scoring each case depending on the gap, match, mismatch penalties. And then lastly, in order to enable the traceback, we need to remember the choice of who gave us the maximum score or the minimum penalty. So we have to remember which one of three cells led to that maximum. And because this is only three-way choice, this is actually fixed rather than having to remember an order of n size, which would lead to much more space needs, whereas this is order of one for any one position. So here's a very simple example. We're basically starting at the top left here. We're traversing all the way to the bottom right. These are very simple sequences, AGT, AAGC. We're initializing at the top left with a penalty or a score of 0, and then we're updating things as we go through, and then the terminations at the bottom right. So what is that update? If we add all of the gap penalties, then we can only traverse, again, in a Manhattan grid, basically go through and arrive at the bottom, each time paying the fixed gap penalty. So any of these paths have exactly the same score, -2, -2, -2, -2, -2, -2, -2. And then this is the termination at the bottom right. When we start adding the matches, we basically see that this diagonal entry here, where you're using the A from both top and left sequences, this diagonal entry, again, using an A from both the top and the left sequences, this diagonal entry here, using a G from both the top and left sequences, are only matches. So that basically gives us a +1 score for each of those. And then all of the mismatches are, again, the diagonals, where we're matching, for example, a T to an A, and that's a -1, a G to an A, that's a -1, and so on and so forth. So that gives us two optimal paths. One of them is moving through here, effectively, matching together A and G, and then having a gap, either immediately or before, and then a mismatch between T and C, and that gives us a termination at the bottom right with the optimal score. So the path can be filled in with the scores. So here, the maximum score is given as 1 because I'm choosing between a score of -2 a score of a score of -2 with an additional penalty of -2, which would be -4, a score of -2 and an additional penalty of -2, which would be -4, or a score of 0 with a reward of 1, which would be 1. So between -4, and +1, we basically choose +1. Here we have similarly the score for this entry can be either the choice between -4 plus -2, which gives us -6, 1 -2, which gives us -1, and then -2 plus 1, which gives us -1. So regardless of which of these two paths we take, this is -1. And then the optimal choice doesn't matter. We can just choose one or the other and then save them as optimal. We could also include a vector of whether each of the choices, each of these 3 dots was chosen as optimal, and basically have that vector be 0, 1, 1, basically saying that this was not optimal, and these two were both optimal, which would allow us to then construct multiple paths on the way back. To fill in this entry here, we basically can choose between -1 plus 1, or 0 -2, or -3 -2, so -5 -2 or 0. So we choose 0, and then over here, again, we have a choice between -1, -2, which gives us -3, 0 -1, which gives us -1, -2 -2, which gives us -4. So the optimal path is basically the optimal score is the score of -1. And then to follow back, to trace back the path, we can basically follow back the red pointers that we have saved to basically walk either this way back or walk this way back. Either one of which would basically give us the same score with an alignment of A to G, whether that gap is at the beginning or in the middle, whether this A gets aligned or that A will get the same score. I hope this is clear. So now this is how we trace back the pointers. So for every location, we always remember the maximum, regardless of whether that location is ultimately in the path of maximum score with a global alignment. For any prefix alignment, this basically gives us the path that gives us that optimal prefix alignment. So you can see here in red, all of the optimal paths, only one of which leads to, actually 2 of each lead to the bottom right entry. And we trace back from the bottom right entry to these loop here. So these are the two optimal paths. This entire procedure is so well defined and so codified that we can actually code it up in Excel. So I will link an Excel spreadsheet that I've generated to actually construct alignments on the fly based on this. So you type one sequence here, you type the other sequence here, then you're using the concatenation function to fill out the corresponding sequences for each of those, or each of the prefixes. So this is the prefix T, the prefix TA, the prefix TAA of that sequence. And every entry here gives us the optimal score of aligning that prefix to that prefix. And at the bottom, we get the optimal score overall. This is based on mismatch scoring matrix that basically penalizes transitions less than it penalizes transversions. Transitions are penalized with a 0 score. Transversions are penalized with -1. And then matches are rewarded with a score of 1. And then here we have a gap penalty of -1, which you can, of course, edit by simply changing that spreadsheet. So to fill in this matrix, we need several additional matrices. So basically here, actually this matrix can be filled in quite easily. This gives us now the optimal score. Actually, sorry, this matrix here is the raw match or mismatch for these 2 characters. So T matches a T, that's a 1. A matches an A, that's a 1. A matches an A, that's a 1. So right here, we have the matches and mismatches. And our goal is to traverse this matrix, collecting as many of the matches as possible and paying for as few as the mismatches as possible. Okay. So that's this matrix. It basically gives us just the single character score by simply looking up here. In this matrix here, we basically have the sum of these scores using only gaps down here or matches and mismatches. And you can see here, the optimal score is 6 by basically going through this algorithm. So let's see if I have all of the functions laid out. So over here, we're basically remembering what gave us the optimal solution, whether it's only diagonally up, whether it's only to the left, or whether either to the left or diagonally up, or sometimes either above and diagonally up, and so on and so forth. So this is a visualization that basically tells us, when I start here, how do I trace back? The maximum choice was given diagonally, diagonally, diagonally to the left, diagonally, 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 either to the left or diagonally. So we can just keep going up diagonally and then end up here. And then this is what you see here. And then the choice that we had over there is basically shown as 2 different entries on that optimal path. So this is the dependency tree that basically tells us how each cell is computed from the other ones. And these are the actual formulas. So basically, S1 is this, S2 is this. This is the final alignment with a gap here and a gap there. This particular entry is computed by looking up in this alignment scoring matrix, whether it's a match, basically what is the match score of this. And this basically gives us the local score of matching these characters, S1I and S2I, not prefixes, just individual characters. This one gives us the max alignment score of aligning these prefixes by basically choosing the maximum of these 3 choices, of basically paying the corresponding penalties from the corresponding entries. This one here concatenates, pointer up, pointer to the left, and pointer diagonally, depending on which one gave us this maximum. So if this maximum that we just computed in AD15 is in fact matching AD14 plus this, or AC15 plus that, or AC14 plus that, then this basically points to the corresponding, it lights up the corresponding bits, if you wish. And then this is finally constructing the path. So basically, is ij part of the optimal path? Namely, are the characters aligned to each other in an optimal path, which simply also counts the number of optimal paths and alignments, just because we can. So instead of just putting a 1 or a 0, we basically have the number of paths that go through this particular position. So over here, we have 1, and then here we have 2, and then this increment all the way to 5. So there are 5 total optimal paths from this position all the way to the end. And then lastly, this is actually constructing that alignment that you see up here by effectively concatenating the corresponding letters from each of the top or left sequences. And it constructs the optimal path for sequence SI by adding in characters or gaps to increasingly large suffixes and arbitrarily choosing one path from multiple are nested. And then you can actually find this in this dropbox link. You can construct the optimal alignment for sequences 2 similarly to S1, and this simply generates S2 and S1. So play with this, it's kind of fun, and it gives you a lot of intuition. So lastly, to construct the path, basically we know how to compute the best score. We need to remember where it came from so we can trace back through the matrix. And now the time needed is to fill in this entire matrix, which is order m times n. For every entry, we only spend constant time. So the total time is simply the number of entries. And then the space needed is actually order nm, because we need to trace back and remember all the pointers. So the last section is to basically look at some additional variations of dynamic programming. In particular, what we can do is realize that these optimal choices, these optimal paths, very frequently go close to the diagonal. If I veer too far from the diagonal, I will accumulate just too large of a penalty in gaps and too large of a penalty in gaps in coming back. So chances are that there are no optimal alignments. The score here in the diagonal here is unlikely to be so strong that it will make up for all of the bad penalties that we've paid to go all the way out there. So in practice, what you can basically do is bound your dynamic programming matrix. Instead of looking at the entire m by n matrix, or n squared matrix if you wish, for sequences of the same length, what you can do is only compute a diagonal of width k surrounding the, you know, x equals y line, if you wish. And that allows you to simply, you know, have exactly the same initialization, but, you know, you simply don't bother defining things that are way off the diagonal. And then you have the same iteration, only, you know, at some point you simply don't compute anything when you go out there. Okay. So an important question is, you know, hey, you just went from order n squared to order n, or kn, if you wish, where k is the width of that sequence. Could you possibly do better? Are there any other tricks or ways of having a faster computation than n squared? And this has remained an open problem for a long time. And in fact, Piotr Indyk, who was one of the co-instructors for the course in previous years, basically, and he's a professor in theory here at MIT, basically said, hey, can we actually show that this is not possible? So he basically reduced this orthogonal vectors problem to pattern, and then reduced pattern to edit distance, and therefore proved that edit distance is a Seth-Howard problem, effectively showing that doing an algorithm that's better than n squared is probably not a very good term project. So, you know, a lot of evidence points that these problems are indeed impossible to solve in any faster way. The last question that often comes up is, do we really need to keep the entire matrix here? So basically, as we're going through, we can compute the score by not storing everything, but then to trace back, we need to store everything. So one of the questions is, can we actually do dynamic programming linear space without storing the entire matrix, which can be quite cumbersome. So if you're trying to do linear space alignment and you're traversing column by column and filling in your matrix, then effectively all you need to remember is your previous column, because you're only using these three entries. And if you only store the previous column, you can basically have these three entries at every position. So all you need to do is allocate column 1 and column 2. And then as soon as you're done with each iteration, just free the previous column that you no longer need and only keep the column right next to you. So that actually gives you linear space computation, which of course still order n squared, just because we actually just proved that you can't do any better from that previous paper. But you need to still maintain some information about the pointers. So the question is, can we do better? Can we somehow achieve this traceback without storing a full matrix of pointers on the way back? And the answer is basically known as the 4 Russians algorithm, and it's something that students in class have often come up with. So basically the key idea is that you're going to be running your computation forward to the midpoint, and that will give you all of the scores for all of the places that go through here. And then you're going to run your algorithm backwards from the right to the left, giving you the optimal scores of all the paths aligning suffixes of S1 and S2. And then by simply summing up the 2 columns that you've just computed, you effectively get the optimal score at every one of these positions. And then you can choose the optimal one and then recurse and re-subdivide your matrices. So here's the idea. So how do you find the best back pointer for the current column? Using only 2 columns of space, we can basically compute all of the scores all the way to here. And then, of course, remember all the back pointers from here. And then, using the reverse computation from the right to the left, we can basically compute the optimal scores here for aligning the suffixes going all the way to the end. And then we're keeping the pointers there as well. And then, combining the 2, we can basically say, what is the optimal score at this position, and what are the optimal pointers? So we can basically save that, and then recurse. Once we know what exact position we're going through at this location, we can basically store this in a linear vector that basically remembers at every position where was the midpoint that we went through, and then recursively compute this, effectively finding the midpoint here and the midpoint there, and then finding the midpoint here, the midpoint here, and the midpoint here, and the midpoint there. Here's where the analysis is kind of cool. The top matrix, of course, costs us order n times m. Each of these only costs us half of that. So it's basically, you know, we're ignoring these two boxes and we're only paying for these two boxes. And then within each of those, we're only paying half each time. So it's effectively the full MN matrix, and then half of that, and then a quarter of that, and then an eighth of that. And that actually becomes a geometric series that effectively reduces all the way down to, let's see, I hope I've been saving audio. That reduces to this linear operation. All right, so this is the lecture for today. Basically, we learned about dynamic programming, the key idea of reusing computation, ordering the subproblems, and then filling the table of the subproblem results, and ultimately reading the table instead of repeating the work. We saw a very simple example of Fibonacci, and then we saw a much more complex example of sequence alignment, where we basically looked at all of the different ways of formulating the problem, from edit distance, varying scoring functions, and ultimately ended up with this dynamic programming matrix, where we found this very nice duality between matrix traversal path and optimal alignment, where every path through that matrix corresponds to exactly one optimal alignment. On Thursday, we're going to look at variations. We're going to look at local and global alignments, affine gaps, and various speedups. And we're also going to look at semi-numerical alignment, hashing, and database. So this is the lecture for today. Thank you for listening, and then I'll see you guys on Thursday. You can email me your questions if you want, and I can post a video reply for all, or I can just cover this briefly at the beginning of the lecture on Thursday, and then you can ask me questions. Thank you.